Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to continue studying probability, and we're going to get into a little more complicated type of problems, but not too bad, things that are going to be clear by the end of this lesson. And the topic today is going to be the addition rules of probability. Okay, another way to write that is we're going to be dealing with problems that have two events, not just one, but two events, and we're going to be interested in the probability of either one of those events happening. So basically event A or event B, okay? And we're going to talk about it and walk through the problems here and get you squared away on that. So an example of that would be you have a deck of cards and the probability of pulling an ace, you can calculate that. The probability of pulling a club in general, you could calculate that. What would be the probability of either one of those things happening? So we need to figure out how to do that when we have two or more events happening in the problem, okay? So what we're going to do here in this problem, in this section, is we're going to always have two or more events, and that's what we're going to start talking about here. So consider two events, A and B, okay? And if we just want to talk in terms of pictures before we actually get to any math, we'll draw our Venn diagram, okay, that we talked about. And if we have two events in there, I told you the Venn diagram is going to become important. Event A, we can write as a circle that we've been talking about, event A, okay? And event B, let's say, kind of overlaps a little bit. This is called event B. Okay? Event A and event B. Now, event A is sitting in here and has a certain probability of occurring. And event B, which is this entire circle, has a certain probability of occurring. And notice that these two things overlap a little bit. That means that there's a certain percentage probability of events there that both of these events can actually happen together. Okay? So an example of this would be, just a general example of these two things, is if you have a deck of cards and you pull an ace out of that deck. Okay, that could be event A. And event B could be you pull a club, in general, just any club from the deck of cards, okay? Well, there would be a probability that you'd pull an ace, okay, let's say. You could pull an ace. That could be this probability, okay? And then this probability here, you could pull a club for event B, a club. Well, obviously there's a probability associated with pulling an ace, and there's a separate probability associated with pulling a club. And notice though that they intersect here, okay? All this means, this part right here, is that it's possible for both of these events to happen at the same time, okay? So the probability of A, and here's a funny symbol I'm going to explain to you here, intersection, that's what this upside down U means, intersection, A intersected with B means A and B, okay? Would be the probability of the two things laid on top of each other like that. So you write this as probability of A and B. You need to get in the habit, anytime you see A with this upside down U and B, you need to always in your head replace this A and B, A and B, A and B. This means intersection, which means both of them happen together. That's why I've only shaded the intersected region. So if I have an ace for this probability, for this event, and another event would be just pulling a club, then the intersection of the two would be the ace of clubs. If both of them happen at the same time, that I pull an ace and I pull a club, the only way to do that is to get the ace of clubs. So that it's possible for these two things to happen, okay? An example of two things that, we're kind of jumping ahead a little bit, but it's actually very possible that two events cannot happen, for instance, at the same time. For instance, event A could be flipping a heads on a coin. Event B could be flipping a tails. Can those two events happen at the same time? I mean, no, they can't. You flip the coin, you get either heads or you get tails. You don't get both. So there would be no intersection if you were going to draw the Venn diagram of those two events. But in this event with the ace and with the club, there's definitely a way to have both of them here. Okay? Ace of clubs. So I'm just going to write that here, ace of clubs. Just to remind you of how that could actually happen. Now let's go off and let's draw another Venn diagram of something similar, but not quite the same thing, okay? So let's say I have event A here, and event B, again, it also intersects. There's really no, let me go ahead and redraw this just to make it totally clear for you, because there's really no significance to the size here. I'm just drawing something to show you. Here's a circle, and here's this, okay? So this, again, is event A, and this is event, again, B. Nothing is different, okay? Now, what if I'm not interested in the intersection of the thing, A and B? What if I'm interested in A or B happening? So either one of these events happening. Well, that would be the entire shaded region of event A. It would also be the shaded region of the intersection, and it would also be the shaded region of B. So the way you would write this, it's called the union. And it would be the probability of A union with the U of B. Okay? And the way you would write this is probability of A or B or both. All right? So basically what you have is and or, okay? Over here, the probability of A and B occurring in exactly the same experiment is only the intersection of these two probabilities when they both occur. Probability of A or B or both is the probability of A happening, the probability of B happening, and of course if they actually happen at the same time, that's fine too. That's usually what we say happens. In general language, when we say A or B, usually if they both happen at the same time, that's fine too, okay? And that's just generally what we mean by or. So an example here would be if A is pulling an ace and B, just like before, is pulling club, okay? How could this happen at one time? A union with B, okay, would be any ace that you pull or any club you pull. Either one is going to give you a success. So contrast that back over here when we were looking at here. If it was A and B, in my single pull, the only way I get a success if it's an ace and it's a club, so it has to be the ace of clubs. Over here, because it's or, I pull an ace or I pull a club, and either one of those is a success. So if I pull an ace of spades, it's a success because A or B. If I pull a 7 of clubs, it's still a success because I pulled a club and I'm looking at A or B. Okay, so it's very simple stuff you've dealt with in language. The Venn diagrams are just used to kind of graphically show. The and is the intersection of these two things. The union, or what's also called the or, you usually call it the union, that's why you have a U here, is A or B or both, of course, in the center. There's one more thing I want to talk to you about, and I've hinted actually about it already, but I'll go ahead and formally write it down for you. Another Venn diagram. Let's say you have event A and event B. There's no overlap between this thing. This is event A and this is event B. Okay? So what we write down is we say if A and B don't intersect, which just means that it's impossible for A or B to happen, A and B to happen at the same exact time, then we call it mutually exclusive. Okay, it's a very important little definition. You'll see it running around your books. So they basically cannot happen at the same time. And you represent that on the Venn diagram by showing that there's no intersection between the two. Okay? So an example of how that could happen would be is if I'm in a deck of cards, let's say, if event A is pulling an even number, okay, and event B is pulling an odd number. Okay? If event A is the probability I pull an even number, and event B is pulling an odd number, there is no way that I can pull a single card from a deck and have it be even and odd at the same time. Those two events cannot intersect. There's no overlap between them, so they call it mutually exclusive. Another example of that would be the coin, flipping heads or tails. You get heads or you get tails. There's no way you can get both in the same outcome of an experiment. It could be also the weather. Either it's going to rain or it's not. There's two events there. There's no way that you can have at one moment in the day that it's both raining and not raining. I mean, there's just only one way that can happen. So in the Venn diagram, if they're not overlapping, those are mutually exclusive events. So briefly before we go on, Venn diagram, event A, event B, if there's some intersection here in the middle, and we're only looking at that, that's what's called A intersection with B. The probability of A and B occurring, that would be like the ace of clubs, have both occurring at the same time. I pull a single card, I get an ace, and it's also a club, ace of clubs, A and B, okay? If I have A or B here and I'm looking at what's called the union of these two things, that means A or B, or of course both happening. Okay, there's some intersection here, but in this case I'm interested in A happening or B happening or both. Event A could be pulling an ace, event B could be pulling a club. A union with B, or A, also called A or B, is any ace that I pull from the deck or any club I pull from the deck. Either way, I get a success, okay? And of course there's mutually exclusive, when event A and event B actually have nothing in common with one another, and it's impossible for them to happen at the same time. And I gave you some examples of that. That would be what would be called a mutually exclusive event. So now what we're going to do, since we've introduced two events happening in sort of the same experiment and give you some idea what these Venn diagrams kind of look like, now what we're going to do is I'm going to write it down. I'm going to show you how to calculate the probability of two events occurring, A or B. Okay, A or B. A lot of times you'll be given a problem where you'll have to pull something from a deck of cards or something else. What's the probability of either one of these things happening? How do you do it? Okay, well, when you think about it, just before you even write anything down, if you think about it, if I asked you, what's the probability of pulling an ace from the deck or a 2 from a deck? Well, you know how to calculate the probability of pulling the ace out of the deck by itself, because there's 4 aces in the deck, that's 4 successes, and there's 52 cards, so 4 over 52. That would be 1 over 13. There's 1 out of 13 chance that I'm going to pull an ace, okay? Now, what's the probability of pulling a 2, okay? It's the same exact probability because there's 4 2s in the deck, and there's 52 cards, so again, it's 1 out of 13, okay? So, if I'm looking for the probability of either one of these things happening, I mean, I know the probability of the ace is 1 out of 13. I know the probability of getting a 2 is 1 out of 13. The probability of either one happening has got to be greater than that. Got to be greater than either one individually, because now I'm not only concerned with the ace, but it could be ace or 2. So it has to be greater. So the short answer is you add them together. Okay, you add these two things together, and that kind of makes sense. You add them together to get the total probability when you're talking about two things, either one of which can happen. So that's basically what you're going to do. You're going to be adding these probabilities together, but there's one little gotcha that we have to kind of work with a little bit here. I'm going to show you where it comes from. It's not quite so simple as just adding the two things together all the time. So let's work through that right now. Okay, what we're going to talk about here is, a lot of times this will be called the additive or the addition rule for probability. The probability of A union with B, which just means A or B. That's all that means. Okay? Is going to be equal to the probability of A occurring plus the probability of B occurring. That's exactly what we just talked about. The two cards from the deck, you add them up. But there's one more thing here, minus, and we're going to show you where it comes from, the probability of A intersection with B. And don't forget, this is just the way of saying A and B. So, before I show you where that comes from, the probability of A or B occurring is the probability of A plus the probability of B. This part should make sense to you, but you're subtracting off the probability of both of them happening at once, and that part is not clear unless you do a little bit of extra explanation. Okay, so let's do that right now. Let's look at a quick Venn diagram of what this would look like. Okay, here's a Venn diagram. Okay, here is event A, here is event B. Okay, so I'm going to put an arrow. This is A, and this is B. Okay, this is event A and this is event B. Now look at what's happening here. We're assuming in this problem here that there's some overlap. So these two things are not mutually exclusive. They can occur at one time, okay? Because we have an overlap. We're showing that they can both occur at the same time, okay? Event A, the probability of it, is governed by this entire circle. Everything inside the circle, basically the area of this whole circle, is effectively the probability of A occurring. The probability of B is also the area of this circle, okay? So if I'm looking for the probability of A or B, which is what I'm looking for, what I really want to know is the probability of both of these things happening, including the part where they cross. Okay, that's what I want. I want the area of the shaded region. That's going to be the probability of A or B occurring. Everything here inside the shaded region here. Okay? Now, work with me here and use the logic. If the probability of A is this circle, this entire circle, and the probability of B is this entire circle, okay? If I just added them together, I'm going to double count this center region, okay? And that's why you have to do a subtraction here, okay? The probability of A is the entire circle. So I'm going to count this part as part of probability of A. The probability of B is this circle here, and because they're overlapping, if I just added them together, I'm basically going to count this central region where they share some common ground here. I'm going to count that 2 times. One time in the probability of A and one time in the probability of B. So I'm going to double count it. Okay? So in order to get rid of that double counting, I'm going to subtract that off. And what is this? This shaded region here in the center? This is the probability of A and B. Remember, this upside down U is A and B. Okay? So in order to fix the thing, A or B is the probability of A plus the probability of B minus this center region. Okay? Now, you're not getting rid of this center region by subtracting it. You're just subtracting the double copy because you counted it once with probability A and also once with probability of B. We subtract it off 1 time, so in the end, we actually get the full shaded region here. That's where it comes from. And if you don't know that, it just kind of looks a little bit odd why you would ever do that. Okay? Now, this is the general form for the probability of how you calculate the probability when 2 events, when you're looking at A or B. Okay? A plus B minus A and B. Okay? But there's a special case that this looks a little bit simpler for. Okay? If A and B are mutually exclusive, okay? And what does mutually exclusive mean? Okay? Mutually exclusive means that if I draw a Venn diagram, okay, then A and B do not intersect. There's no intersection here. Okay? If A and B are mutually exclusive, then this reduces. This equation that we wrote here actually reduces. P A intersection with B is equal to the probability of A plus the probability of B. And you don't subtract anything off because there's no intersection here to begin with, so there's nothing double counted. Probability of A plus probability of B if they're mutually exclusive. So a lot of books, confuse students because they present this rule, and if you don't really understand everything in here, you might just memorize that. And then later it says, oh, if these are mutually exclusive, here's another rule. And it looks like they're 2 different rules. But in fact, they're not 2 different rules. They're exactly the same rule, okay? What I advise you to do, what I'm going to do in all these problems, is just use the top rule. Okay? When you calculate the probability, you're going to calculate the probability of A, you're going to calculate the probability of B, and then when you try to calculate the probability of A and B, if they happen to be mutually exclusive events, you're going to get 0 for this because there's not going to be any A and B involved. There will be no way for them to overlap. So based on the problem, you're going to get 0 for that, and so you're just going to get the answer. So rather than have you memorize 2 things and try to have you have all these different rules in your head to keep straight, just remember this one because this is the real rule. This just drops out to 0 in certain cases when you actually have a mutually exclusive events there. Okay, so let's get to some problems. Okay, we're going to start out with the simplest problem I could possibly come up with to explain this, and then we'll get to the more complicated problems. You flip a coin. Okay, what is the probability that you will get a heads or a tails when you flip this coin? Heads or tails. Now, before we do anything, just think about what the problem is saying. You have a coin, you flip it. You know from experience it's going to land on heads or tails, no matter what. I mean, it's not going to land right on the edge. Let's just pretend that that's not going to happen, okay? It's going to land on heads or it's going to land on tails. So you know the answer to this problem is going to be 1. Because it's going to land on heads or tails. So if the events that I'm looking at, if a success is heads or tails, I'm always going to get one of those. So the probability of the answer is always going to be 1. But let's use our newfound knowledge of how to do this thing mathematically and bang through a very simple problem, and then we'll go to more complicated problems. Okay. So my event A, the way you do this is you always label your events. You get a heads from your flip. Event B is you get a tails from your flip, okay? Heads and tails, okay? Now, just to give yourself a frame of reference, it's always kind of helpful if you can think about it to draw a little Venn diagram. First thing you need to ask yourself, is it possible for these 2 things to happen at the very same time? The answer is no. There's no way to get heads and tails at exactly the same time. So these are actually mutually exclusive events. There's no overlap between them because heads and tails, there's no way you can have heads and tails happen at the same time. Okay? So we use our newfound knowledge here. The probability of A union with B which is just simply A or B, that's what that means, okay, is going to equal to the probability of A plus the probability of B minus the intersection here, which we know is 0, but we're just going to, for grins, just write it down, probability of A intersection with B, also known as A and B. So you can write this as A and B. I'm trying to help you remember what these things mean because I know these symbols are hard to remember, okay, at first. Even I get confused looking at them sometimes, okay? So the probability of A union with B, which is A or B, okay? What's the probability of A occurring? What is the probability of getting heads? I think you know from the previous section that's going to be 1/2. There's one way I can get a heads, 2 possible events. The probability of event B is the same thing, 1/2, because tails is the same probability, minus the probability of both of them happening at exactly the same time, A and B. Well, the probability of both of them happening at the same time is 0, okay? So the probability of A union with B, which is the A or B, is just going to equal 1, which means that there's a 100% chance it will definitely occur that A or B will happen, one or the other. So with 100% certainty, we know what's going on. So that was a very simple problem just to kind of give you the hang of it for something that we're all very familiar with. Now let's go into some problems that maybe you're not so familiar with and keep going. So the next problem says you have 2 dice, okay, and you roll them at the same time, okay? What is the probability that the sum of those 2 dice is going to equal 3 or 4? Okay, so we look at the probability of getting a 3, of the sum of the dice being 3, or the sum of the dice being 4, okay? So we start out always by labeling our events. Event A, the sum of the dice is equal to 3, and event B, the sum of the dice is equal to 4, okay? And what I'm looking for, what the problem said, is the probability of A union with B, which is the probability of A or B happening, okay, is going to equal the probability of A plus the probability of B minus the probability of A and B. A and B, that's what this means, okay? So this is A or B, and this is A and B. Now, let's just think about this for a second, okay? If I'm going to draw a Venn diagram of this, and event A is getting a sum of 3, is it possible if I roll these dice for event A and B to happen at exactly the same time? Of course not. You cannot roll dice and get a sum of 3 and a sum of 4 at the same time. So these are mutually exclusive events. There's no intersection here. So this is actually going to be 0 eventually when we calculate everything. We're just writing it down here because that's the general rule, okay? All right, so now what we need to do is we need to calculate the probability of event A happening and the probability of event B happening and add them up. And of course, we're going to be subtracting 0, and that'll be, that'll be the final answer, okay? So what would be the probability of A? That's my next question to you, okay? Let's switch colors here. The probability of event A. Event A is getting a sum of 3. Now, the way you really need to do this is start thinking about this. If I've got, here's die 1 and die 2. How can I roll these dice to get a sum of 3? Well, if I get a 1 here and a 2 here, I'll get a 3 sum. If I roll a 2 here and a 1 here, I'll get a sum of 3. I do not believe there's any other way that you can roll those dice to get a sum of 3. I don't believe, because you can't roll a 0, and anything more than these numbers is going to give you a number bigger than 3. Those are the only 2 possible ways these dice can fall to give you a sum of 3. So the probability of rolling an A is going to equal 2 outcomes to equal my success, okay, divided by the total number of possible outcomes of these dice. Now, it's a 6-sided dice, so how many possible ways can the dice fall? 6 times 6. 6 sides on the first die times 6 sides on the second die for 36 total ways in which those 2 dice can fall. And this is done exactly the same way as the telephone numbers in the first section with the fundamental counting principle. 6 ways the first event can happen, the first dice, 6 ways the second dice can fall, 36 total possible combinations. So you get 2 over 36 is what I'm really getting at here. Okay, 2 over 36. Now what's the probability of B happening? Which is getting a sum of 4. So let's go back over here and say here's die 1 and die 2. Okay? And what I'm trying to find out is how can I get a sum of 4? Well, if I get a 1 here and a 3 here, I'll get a 4. If I get a 3 here and a 1 here, I'll get a 4. And if I get a 2 here and a 2 here, I'll get 4. Okay? So I believe there's only 3 ways to get a sum of 4. I don't believe there's any other combination you can choose to get a sum of 4. Okay? So the probability of B happening, which is to get that sum, is going to be 3 possible outcomes over, again, 6 times 6 for 30, because there's 36 total ways the dice can fall, so 3 over 36. So the probability of A was 2 over 36. The probability of B is 3 over 36. So then the probability of A union with B is the probability of A plus the probability of B, 2 over 36 plus 3 over 36 minus probability of A and B. A intersection with B is A and B. Can these things happen at the same time? No, they can't. There's no intersection between these two events. There's no way they can happen at the same time. So A and B give me a 0. So the probability of A intersection with B, A or B happening, is 5 out of 36. 5 out of 36 times, 5/36. That is the answer. Okay, so what we did is we calculated the probability of each event individually and we added them together. There happened to be no intersection, so the answer just kind of fell out there. So in general, you're adding the probabilities and you're subtracting off any intersection that occurs between them. Okay, the next problem says one card is picked from a 52 card deck. Okay, what is the probability that the card is a heart or a number card greater than 6? Okay, so this kind of problem has a lot of information in it and you really need to pick it apart to understand what it's asking you to do. First of all, you see the word or in there. So you know that you're going to have two probabilities or two events, either one of which can happen, gives you a success. Okay, one card is picked, only one, from a 52 card deck. What is the probability that that card is a heart or a number card greater than 6? So, you know, you're not going to figure this out by thinking about it all day. By the way, that's exactly true. You know, a lot of times you'll read these problems and your first thought is just going to be to think about it and think about it and think about it. Maybe somehow it'll come to you what the answer is, because, you know, you may lock up. Don't do that, okay? Just start with what you know and write something down and start working through it, because these problems, you're very unlikely, very low probability that you'll actually be able to figure out the answer just by reading it. You're probably not. You just need to start writing what you know down to be true and working from there, okay? So what I always do, because I'm comfortable doing it, the very first thing I do is I label my events. Event A is you get a heart, okay? And event B is you get a number card, so no jacks, kings, or queens, or anything else, number card greater than 6, okay? Number card greater than 6. Now, before we actually go any further, let's just, you know, if you can, draw a Venn diagram to kind of help you visualize what's going on, okay? Event A is right here, okay, which is getting a heart. Is it possible for A and B to happen at the same time, okay? Can I have a heart and also a number card greater than 6? Of course you can. You can pull a 7 of hearts, or an 8 of hearts, or a 9 of hearts, or a 10 of hearts, and that would be a valid intersection of these two events, with A and B happening at the same time. So this Venn diagram is actually going to have some overlap, unlike the last one. So it'll be a little bit more interesting. Now the next thing you do to kind of continue working through it is the probability of A union with B, which is A or B. I'm going to continue helping you out here by writing it A or B, just to kind of help you remember that that's A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. And I explained why you're doing the subtraction earlier. You're doing the subtraction because you have double counting of this center region here from probability of A and probability of B. You're double counting the intersection here. So in order to get the union of both, you want to subtract off one of those intersections. So that's what we're doing. So we have to calculate the value of A, the value of B, and the intersection here. So let's do that. Okay. What would be the probability of A? The probability of event A is pulling a heart from the deck. So how many hearts are in a deck of cards? Okay, there's 13 hearts in a deck of cards out of 52. There's 13 out of 52. What is the probability of event B happening? Event B is getting a number card greater than 6. That means I can pull a 7, an 8, a 9, or a 10. Okay, that's 4, 7, 8, 9, 10, but there's all different suits. There's 4 suits, so there's 4 cards times 4 suits is 16 total cards for success. I have 4 cards, 7, 8, 9, 10, but I have 4 different suits, so there's 16 total cards to make B a success, again, out of 52 cards. Okay, so that's what the probability of B is. What is the probability of A intersection would be, which is A and B? So A and B would be, you get a heart and it's a card greater than 6. So you have 7, 8, 9, and 10 of hearts. So you have 4 cards, 7, 8, 9, 10 of hearts. There's only 4 cards like that out of 52. Okay? So we have everything we need. So the probability of A intersection with B, A union of B, which is A or B, is going to equal probability of A, which is 13 over 52, plus the probability of B, which is 16 over 52, minus the intersection of the two, 4 over 52. Okay? And when you actually do this, the 13 plus the 16 minus the 4, you're going to get 25 over 52. And that's the probability. So it's the same kind of thing. You label your event A, you label your event B, calculate the probability of A, calculate the probability of B, calculate the probability of both occurring at the same time, and then use a little relation to get the answer. Okay, the next problem says you roll 2 6-sided dice, same as before, 2 regular old dice that you're used to playing with. What is the probability that the sum of the dice is odd or divisible by 5? Okay, so it's exactly the same kind of problem before where we had the 2 dice. But this one's much more complicated because I'm rolling 2 of them and I'm trying to find out what the probability that the sum of these 2 dice is an odd number or the sum is actually divisible by 5. So I don't know about you, but there's no way that I'm going to be able to find out all the different ways in which the 2 dice can be rolled unless I make a table. Okay, so that's what we're going to do. First thing we do in all these problems is to label my event A. The sum is odd, because this always helps me come back and look at what A and what B are. I would always recommend you doing that. Event B is the sum can be divided by 5. That means divided by 5 evenly, like 10 can be divided by 5 evenly. Okay. Alrighty, and of course we know that the probability of A or B, which is the union, A union with B, is equal to probability of A plus probability of B minus the probability of A intersection with B, which is A and B. So this is or, this is and. Okay? That's or and that's and. All right? So what we need to do is we need to calculate the probability of A and calculate the probability of B. And because everything is involving a sum for the events A and B, what we're going to do is we're going to actually write a little table here. Let me draw a little line. And the way we're going to do this is I'm going to have something like this. Okay? Die 1, die 2. Okay? And what I'm going to have, we'll just go ahead and do it like this. Die 2 can get a 1, 2, 3, 4, 5, or 6. That's the values that he can have. And die 1 can also roll a 1, 2, 3, 4, 5, and 6. Okay? So just to kind of keep things clean, I'll draw some nice little lines through here. And really what we're going to do is we're going to make a table of sums. That's all we're going to do, because we're trying to find all these different cases when the sum is odd or the sum is divisible by 5 or something. And there's really no way you're going to be able to do that unless you have a table of all of the values so you can count up all the times you get a success and so on. Okay? So, die 1, die 2. If I roll a 1 and a 1, the sum is going to be 2. Actually, you know what I'm going to do to make it easy? Easier, I hope. The sum is 2. Okay? 2 and 1 are going to give me 3. 3 and 1 is going to give me 4, 5, 6, 7. 6 plus 1 is 7. So this is going to be a simple table to fill in. 1 plus 2 gives me 3, 4, 5, 6, 7, 8. I think you can convince yourself. 1 plus 3 is 4, 5, 6, 7, 8, 9. I think you can see the pattern. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And 7, 8, 9, 10, 11, 12. 6 plus 6 gives me 12. So I was easily able to fill in the table. Okay? Now, how do we use the table? The probability of event A, the probability that the sum is odd, is going to equal the number of ways in which the sum can be odd divided by the total number of outcomes that you can have. Okay? So, what we're going to have is we're going to count the number of times the sum is odd. So let's just go. You have, going here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 successful ways to get an odd sum over 36 possible outcomes. 6 times 6 is 36 possible outcomes, so 18 over 36. Probability of event B, okay? Probability of event B. What is event B, by the way? Event B is the sum is divisible by 5. How many ways can that happen? Let's go across. Divisible by 5. 1, 2, 3, 4, 5, 6, 7. 7 ways that it's divisible by 5 divided by, again, 36 possible outcomes. So the probability of A, the probability of B. Now, what is the probability of A and B? A intersection with B. Can both of these things happen at the same time? Yes, they can. You can have an odd sum that's also divisible by 5. Okay, so let's go and figure that out. We're looking for the odd numbers that are also divisible by 5. Okay, the odd numbers that are also divisible by 5. So what we're going to have here is, here's 1. This is an odd number divisible by 5. Going down. 2 is an odd number divisible by 5. 3, that's an odd number divisible by 5. 4. Okay, so we're up to 4. This is divisible by 5, but it's not odd, so he doesn't count because we're looking for both. Okay, keep going. We're up to 4. Keep going. This is the same number, so he doesn't count. We don't find this is odd number, but he's not divisible by 5. So there's nothing else in the table that are odd numbers that are also divisible by 5. There's only 4 ways that happen. All the 5s in the table really are the only ways it can happen. So 4 ways out of the 36 combinations. So we have everything we need. Now the probability of A intersection with B is going to be equal to the probability of A plus the probability of B minus the probability of both. So it's 1836 divided by 1836 plus 736 minus 436. Okay? 18 plus 7 minus 4 is going to give you 21 over 36. And you divide the top and the bottom of this thing both by 3. 7 times 3 is 21, and 12 times 3 is 36. So the answer is 7/12. And that is the probability of A or B happening at the same time. The probability that the sum of those two things is odd, or the sum is divisible by 5. So that's a problem that looks very complicated when you first read it, but you have to break it down methodically. Label your events. Okay, write down the relation that tells you what the two A or B, A plus B minus the intersection, and then in order to find the probabilities, you have to do what you have to do. In this case, you have to make a table because there's no way you're going to be able to count all these things without a table. So we made our table. Probability of event A with the odd sums, we counted them up. 18 over 36. We counted the number of times that we had a number divisible by 5 over 36, and we counted the number of times that both of them were true, and then we put them in the formula. And we got the answer there, okay? So we're making some really good progress. These are getting to some fairly challenging problems. So the thing you have to do is read them, understand what they say, label your events, and just work your way through finding the probability of the different events, okay? The next problem says a box has 5 white balls numbered 1 through 5, and it has 5 green balls numbered 1 through 5, okay? You choose one ball from this box at random. Okay, what is the probability that that ball is white or odd numbered? Okay, white or odd numbered. So, a lot of information, same kind of thing, but you know that there's a couple of events going on and we're trying to find the probability that either one of these things happens. So it's an or problem. We're going to calculate the probability of the union of these two events. Okay, The box has 5 white balls, 1 to 5, 5 green balls, 1 to 5. What's the probability that it's white or that I've chosen an odd numbered ball? Okay. So, first things first, label your events. Probability A, choose a white ball. That's what probability, that's event A, okay? Event B is to choose an odd ball, odd numbered, 1, 3, 5, 7, something like that, okay? And what I'm looking for is the probability of A union with B, which is A or B, okay? That I get a white ball or an odd ball. That's basically what it says, okay? So that's going to be the probability of A plus the probability of B minus the probability of A intersection with B, which is A and B. Okay? Now let me ask you a question. Is it possible for these two things to happen at one time? Can I choose a white ball that's also odd numbered? Well, if you read the problem, yes, you can actually. You can, because you have some green balls numbered 1 to 5 and you have some white balls numbered 1 to 5. So it's certainly possible to choose a white odd ball. So if you were going to write a Venn diagram, you would see there's a little intersection point here. So when we get to the point where we have to do the subtraction of the intersection, we're going to have something to actually subtract in this case. Okay? Just like in the last problem. Okay? So let's go ahead and try to find what is the probability of A. The probability that I have chosen a white ball. Okay? So let's look and see what kind of balls we have in here. For the white balls, we have 1, 2, 3, 4, 5, 6. Actually, only 1 to 5. White balls 1 to 5. We also have green balls 1, 2, 3, 4, and 5. So the question is, what's the probability of choosing a white ball? What's the probability of choosing a white ball? How many ways can we choose a white ball? There's 1, 2, 3, 4, 5 white balls divided by the total number of choices in the experiment. There's 10 balls total. Okay? So I'm just going to leave it like that, 5/10. Okay? The probability of B is the probability of choosing an odd number ball. How many times or how many ways can I choose an odd ball? Here's an odd one, here's an odd one, here's an odd one, here, here, and here. So that's 1, 2, 3, 4, 5, 6 odd balls total. Again, 10 odd balls, 10 total balls here. So it's 6 over 10 for probability of getting an odd ball. And what is the probability of A intersection with B? The probability that both occur at the same time. So what I'm looking for here is a white ball that's also odd. How many ways can I choose a white ball that's also odd? Here's an odd one, here's an odd one, here's an odd one. Has to be white, has to be odd. So there's 3 ways to do that. How many balls are there total? There's 10. So 3 out of 10, I'm going to get a white odd ball, A and B. Okay? So getting back to the roots here, the probability of A union with B is going to be the probability of A, 5/10, plus the probability of B, 6/10, okay, minus the probability of both, 3/10, okay? 5/10 plus 6/10 minus 3/10, and when you do this, you're going to get 8/10. 5 plus 6 is 11, minus 3 gives me 8, and you can simplify this. This is going to come out to 4/5 when you simplify that fraction 4/5. So it's the same thing. You get a lot of information in the problem. You really just have to pick it apart. Label your events, write down something to help you do the counting to calculate the probabilities. Probability of A getting the white ball, we calculated. Probability of B getting the odd ball, we calculated. Probability of both, we calculated, and we added A plus B minus the intersection, giving us 4/5 for the total probability of getting a white ball or an odd ball. Okay, for our last problem, it's kind of a lengthy problem, but it's going to be really, I think, instructive. The problem says, the probability that a new school will get an award for its design is 0.16. The probability that that school will get an award for the lowest cost is 0.24. The probability that it will get both awards is 0.11. What is the probability that it will get at least one of the 2 awards? That's the first question. What's the probability that it will get at least one of the 2 awards? And the second follow-up question is, what is the probability that it will only get one of those awards? Okay? So you have a lot of numbers here, a lot of things to think about. We need to pick it apart. The probability that this new school is going to get an award for its design is 0.16. The probability it's going to get an award for its cost, low cost, is 0.24. Probability it gets both is 0.11. So the first part says, what is the probability that it will get at least one of the two awards? You know, half of the battle in probability, I mean, I think you've seen it up till now. We've done lots of problems in probability so far. The math itself is not very hard. It's addition and subtraction of fractions, really, is what it is. You just have to know what to do in order to get over the hump of the challenge here of figuring it out. The math, it's nothing like calculus, or we have a lot of tedious math. It's nothing like that. It's thinking about it, okay? So half of the challenge is reading it and really figuring out what they're asking you. And once you can do that, you can usually solve the problem. So when someone says to you, what is the probability that it will get at least one of the two awards? How could you rephrase that to mean a little bit, something a little bit more concrete for you to wrap your hands around to use in this problem? If I have an award here and an award here, two different awards, and I want to get at least one of the two awards, that means I want to get this one or I want to get this one. Or, you know, I can get both too, that's great, but if I want to get at least one of the two, I want to get this one or this one. So you change the problem. You see, they intentionally phrased it as to get at least one of two awards. Well, you have to kind of mangle that and kind of beat it into a form that helps you change this mentally in your head to, instead of getting at least one of two awards, the way I would say it is, I would get award A or award B. Now I know how to handle that, okay? So the first thing we're going to do for A, okay, is you're going to have an event. A is I get an award for the design, okay? B is I get an award for cost. And what A is actually telling you is I want the probability of A or B, which is the probability of A union with B. Those are just the two different ways of writing the same thing, okay? So instead of saying at least one of the two, I've got something I know how to calculate, A union with B, okay? So what I'm going to have here is, let's go ahead and draw a little Venn diagram and try to write down what we know, and just, you know, it's always good to have a picture if you can draw a picture. Okay, you have award A and award B, and there is an intersection because there is a probability of both of these things occurring. Okay, this is A and this is B. This is award A. Award A, it says in the problem, has a probability 0.16, and award B has a probability of 0.24, and award A and B, the probability of A and B, which is the intersection, A intersection with B, is 0.11. Okay, 0.11, both A and B. So I'm going to put A and B to help you remember that. I'm just drawing a picture. Award A, award B, intersection of the two is that. So now what I'm trying to calculate for problem A is the probability of getting either of these awards. Okay, A or B. So the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. And we talked about where that came from before. You're subtracting this off because when you calculate A plus B, you're double counting the center area, and you only want the area of the whole thing, so you have to subtract off one of those intersections in order to get basically the right answer, okay? Now, this is really easy because we know what the probability of A is 0.16. We know what the probability of B is, 0.24. We know what the probability of the intersection is, 0.11. So you just basically put these things in your calculator and you'll get 0.29. That it will get either one of these, at least A or B or both. That's fine. A or B or both. That's the probability there. And you can see that in this problem, the challenge was not the math. The math was adding three numbers together. The challenge is knowing what to do when you read something like, what is the probability that it will get at least one of the two awards? And translating that to, I want award A or B. That's fine. And then you know how to calculate that. Now the second part of the problem is, says, what is the probability that it will only get one award? So you get, one award or another award, but not both. That's basically what you need to translate that to say. Probability of only getting one award. You need to think about what it means. It means I can only get one or the other, but I do not want to get both. Only one of these awards, okay? So if you think about your Venn diagram here, we've just calculated the probability of getting A or B, okay? What we need to do to ensure that we don't get both is to subtract this center commonality again, okay? We need to subtract it again because in the end, what we're going to be trying to get here, if I'm going to only have one award or another, but not both, what I'm really going to be interested in is A or B, but not both. Okay, that's what we're doing here. This is A, this is B. Okay, and what this problem is saying is I can get A or I can get B, but I am not going to get both. So what I need to do is this thing that we calculated right up above was A or B or both. That's what the whole thing is. Anytime you calculate A or B, you're always calculating A or B or both. That's what you're doing. So in order to subtract out the both part of it and just get A or B by itself, what you're going to effectively get is you're going to get 0.29, which was the answer that we got for A or B or both, and we're going to again subtract off the intersection, 0.11, because we don't want both, okay? And the answer is just going to be 0.18. That would be the probability of getting either one of these awards, but not the common area in the middle, not both, okay? So we've covered some tremendous ground in this section. We've covered what you do in probability when you have two events, and you're trying to figure out the probability of getting one event or another event or both. And basically what it comes down to is you're going to effectively add up these two probabilities, okay? You're going to have to subtract off a term, the intersection between the two, precisely because of the way the probability is defined and in your Venn diagrams, and that's why they're so useful. If they overlap like that, then you're basically double counting that intersection, okay? So when you calculate the or between them, A or B or both, what you need to do is calculate the probability of A plus probability of B and subtract off one of those intersections so that you're not double counting it, okay? And every other problem in this section has been dealing with that. It's just that in every problem you need to go through and calculate probability of A, probability of B, probability of both, and applying that definition accordingly. And that is how you calculate the probability of the union of two events, A or B or both, in probability.